Traditional silicon photovoltaics are designed to capture a narrow band of the solar spectrum. When standard panels lose a direct, unbroken line to the sun, their electrical output drops off a cliff. Our current global solar infrastructure relies on this strict geometric requirement. Arrays must physically face the sun to maintain their rated efficiency. Look at these overcast conditions. Heavy atmospheric interference acts as a physical barrier. Water vapor and thick cloud cover scatter visible light, disabling standard arrays. But an alternative architecture utilizes a different spectral band. It is called AuREUS, an organic luminescent solar concentrator, or LSC, engineered from agricultural waste by a student named Carvey Ehren Maigue. Because UV radiation is highly scattered, this concentrator produces power through indirect irradiance, functioning under cloud cover and in shadow, by capturing the energy standard panels cannot. To understand the mechanism, we must map the molecular physics of the material. We will examine how organic fluorophores extract ambient UV energy, alter its wavelength, and route it to standard photovoltaic edges. This image shows a typical solar installation relying on direct irradiance. The panels are positioned at a precise angle to intercept incoming rays head-on. When solar radiation enters our atmosphere, it undergoes Rayleigh scattering. Lower frequency visible light travels in straight paths and is blocked by solid obstacles like clouds. High-frequency ultraviolet photons behave differently. Hitting suspended atmospheric particles, they scatter intensely. This scattering creates a diffuse radiation field. UV energy bounces off concrete walls, reaches into shadows, and penetrates cloud cover, saturating the environment from every angle. Standard silicon cells lack the optical architecture to process these high-energy, nonlinear wavelengths efficiently. A cloudy day is not a lack of available solar energy hitting the Earth. It is a limitation in our ability to harvest the diffuse ultraviolet wavelengths that successfully penetrate the atmosphere. Standard solar cells require direct, concentrated visible light to excite electrons across their bandgap. If the light is too scattered, the current fails. The solution involves spoiled fruits and vegetables. Specific natural organic compounds, called fluorophores, are isolated from this agricultural waste to act as an optical bridge. During the absorption phase, these organic molecules absorb the scattered, high-energy UV photons present in the environment. This triggers a molecular mechanism known as the Stokes shift. The molecule absorbs the photon, loses a small fraction of vibrational energy, and instantly emits a new photon. Due to energy loss, the wavelength of the light expands. The newly emitted photon downconverts from invisible UV radiation into the visible light spectrum. These organic dyes function as optical translators. They strip energy from chaotic, ambient UV radiation and produce uniform visible light. Scaling up from the molecular level, these organic dyes are suspended throughout a transparent resin pane to form a luminescent solar concentrator. Once emitted within the resin, total internal reflection takes over. The transparent boundaries geometry causes the photon to reflect off interior surfaces, trapping it. This continuous reflection channels the visible light, funneling it outward to the panel's narrow edges. Ultra-thin strips of standard silicon photovoltaics are integrated solely into the perimeter frame. They intercept this concentrated visible light at the edges, generating an electric current. This architecture reduces the required footprint of silicon to the frame alone, while turning the entire transparent surface into an omnidirectional energy funnel. Applying this technology to modern infrastructure expands the potential footprint of renewable generation. Because the AuREUS system captures scattered UV radiation, it is not restricted to horizontal orientations. This allows for vertical deployment on building facades with minimal loss in efficiency. Look at the sheer volume of vertical surface area in a modern city. This space dwarfs the available rooftop square footage, offering a massive, untapped area for power generation. By utilizing the molecular physics of the Stokes shift, we can transform every passive glass window into a highly functional energy harvester. Mastering optical chemistry allows urban environments to harvest the diffuse, invisible energy that already saturates the built environment.